to this lecture, and now we were discussing about the breaking of 3-phase induction motors, and there are 3 methods as in the previous class I told: plugging, DC dynamic braking and regenerative braking, of which plugging we were discussing. The whole idea is of braking is, therefore, if you want to make the machine come to a stop quickly, physically we understand that that energy, kinetic energy to be dissipated fast. Friction alone will absorb that energy, but it will take longer time. So that machine will come to a stop after a long time. Sometimes it is necessary to induction motor to stop quickly in some repetitive work and once again restart it, things like that, where you have to apply electrical braking. And so, the opposing torque, in which direction the rotor is already rotating, must be developed in the machine. So, I was telling that if you have an induction motor with which is supplied with phase sequence AS, BS, CS supply phases, and these are machine terminals ABC phase, then you have to and it will run normal motor. This way it is normal motoring operation. Now, what I will do is this, this is a triple pole double throw switch. So, it will have either this way it should be connected or here it should be connected. Now, here from the supply only you bring it like this. This is AS, this AS is this AS are same, and this you tell CS, and this you tell BS. So, when you want to break the machine, what I am telling, so this is braking, when the switch will be, it was running nicely at steady speed NR with slip NS. Suddenly, I move this switch, which is gang switch, together it will move, bring it to this side. Then you can see the supply phase sequence to the stator is reversed, and therefore, rotating field will start rotating in the opposite direction. At t equal to 0, plugging is executed. What this executed means? It means you have put the switch from here to there very quickly. In that case, what will happen? The rotating field will start, electrical time constant is much smaller than mechanical. So, the rotating field now will move with same speed, but in the opposite direction, and rotor is still moving with the same speed NR here. At t equal to 0 plugging is executed, and at t equal to 0 plus, this is the situation. Rotor is still moving in that direction. Now, as you know, the electromagnetic torque developed by the machine will now act along the direction of the field rotation. Therefore, electromagnetic torque the machine will develop will act in this direction. Now, the question is, at t equal to 0 plus, what is the slip? Earlier motoring operation, this was the slip Ns minus Nr by Ns. At t equal to 0 plus, slip of the motor will be, only Ns has reversed. So, put minus Ns here, minus Ns, minus Nr, Nr remains same and minus Ns, this is the thing. But from this Nr, we know when it was motoring, it was like this, 1 minus S into Ns. I am sorry, this was the thing, Nr equal to 1 minus S into Ns. Therefore, at t equal to 0 plus, immediately after plugging is executed, sleep of the motor will become, if you put this, it will be ns plus nr by ns here, and it is ns plus rotor speed was ns 1 minus s. What is this sleep? At the motoring mode, whatever was the sleep divided by ns. So, if you simplify, it will become 2 minus s. Therefore, the moment plugging is executed, earlier sleep was 0.05, sleep will immediately become almost 1.95, 2 minus s. And how much torque is developed by the machine? Direction of the torque must be opposite, this T must be opposite to NR, and what will be its magnitude? How to calculate? Okay, everything remaining same formula can be used. Only thing, you calculate the torque replacing s by 2 minus s. For example, the simple formula I will write where it is equal to some k s alpha by s square plus alpha square during motoring mode. Now suppose you have done this. So, at t equal to 0 plus, this is called braking torque, T b will be k 2 minus s into alpha by 2 minus s whole square plus alpha square. What else? Because sleep has only changed. Therefore, braking torque can be calculated like this. Graphically, it means that it is like this, that suppose this is the torque slip characteristics of the machine, and we are stopping here at slip equal to 1. This is slip equal to 0, this is torque, and it was motoring. And machine was operating at this point, say at this slip s as a motor. Now, suddenly what I have done? I have changed the supply phase sequence, and I say slip has become 2 minus s. Suppose this is s equal to 1. So, this point is s equal to 2. So, 2 minus s means here at this point, whatever is the torque developed, that should be the braking torque. Or in other words, what I am telling, the torque slip characteristics while sketching, I will not stop at s equal to 1, I will draw it for all s up to 2 using the same formula. Here, how did I get the torque slip characteristics? By putting different values of slip and stopped at 1, because I know motoring mode 1 and we are considering motoring mode. Now, I am in a different situation. If somebody does like this, change the supply phase sequence applied to the motor, keeping the voltage frequency same, then there is a need to compute the electromagnetic torque. If I want to know what is the electromagnetic torque developed by the machine now, I have to read that value from this. This is 2 minus s. This much torque will be produced, and this also it is showing positive torque, but I know physically what has happened, it is actually acting in the opposite direction. This is the TB, electromagnetic torque, but it is opposite to NR. Like this. Therefore, this is called the braking zone. Therefore, often this is the whole range of speed torque characteristics in motoring mode. It can be, as a motoring it is like this, if you have done plugging it will go up to this point. This is the this point is S equal to 2 and this must be, if it is S, 2 minus S will be here, so much little braking torque will be produced and it is expected machine will come to a stop. If it is a slip ring and this is done. Now, to read the value of electromagnetic torque, straight away what people sometimes do, they draw these characteristics also ready. I mean, if you are doing plugging, you know before, then the same torque slip characteristics, it is not mirror image and then flip around the vertical axis. If you draw like this, it has nothing to do with machine operation. What I am telling, if it is operating at slip is, you will say electromagnetic braking torque is this much, you have to come here. Now, I will say if you draw it, that is you fold it around this x axis, slip axis and then take the mirror image, then you will get this curve and this S, this is the initial operating point, load torque it was supplying. Load torque was always in opposite direction to the rotation of the motor NR. If you do plugging, I will say, oh, electromagnetic torque at that time will be this one, that is all. Same thing I am telling in a slightly better way, so that you can read the values very quickly. And your, if there is an active load there, then I will say total braking torque may be this plus this at that time acting. Okay. So, you execute plugging, same torque expression I am using, assuming steady state thing formulas which may not be very exact thing I am telling you, there will be transients, but anyway it gives you fair idea what is going to happen, steady state only equations, same equations as if I am pretending holds good there. Okay, people do it, you get the idea of that. But after, so machine will start slowing down at a much faster rate, it looks like. Now, suppose you have made this switch from left to right side and kept this switch there, what is going to happen? Eventually, machine will come to stop, no doubt, but then start running in the opposite directions. Therefore, if you want to really stop the motor, then you must have some sort of speed sensor which will sense, okay, 5% speed it has come, then you disconnect it from the supply. That is, this mechanical switch I have put on this, or by watch you should look at the rotor speed. Okay, you have put it that side, when speed has come close to 0, switch it off in the neutral position, then it will come. But some arrangement is to be made if you want to make it a automatic process, electrical braking by plugging. The magnitude of this braking torque can be increased. If it is a slip ring induction motor, very easily it can be done. What you do, when you from motoring mode you want to go to braking mode, you put it here and at the same time you insert some resistance in the rotor circuit. Suppose I do this switching and then automatically some equal values of resistance are put in the rotor circuit. In that case, how to calculate braking torque? Braking torque will be, see, this is T, This is with normal rotor resistance, this and this, but after you have executed plugging, this characteristics will look like this. Something like this with extra rotor resistance, and your braking torque will be then this much. Therefore, you can increase the braking torque by perhaps connecting a resistance in the rotor, and this curve also can be drawn reversed and flipped, so that the reading of this braking torque can be easily estimated. I am not drawing that, you have understood the idea. If it is a cage induction motor, of course, there is no scope for increasing the braking torque, but during that plugging operation there may be sudden inrush of current due to transients. So, to limit that current, people connect some reactance or resistance in series with the stator, thereby further decreasing this braking torque available. I mean, these are the things. So, it is called plugging. Plugging means you reverse the supply voltage polarity. Only thing is, when the machine comes to a stop, you should be alert, you have to disconnect the motor from the supply, otherwise it will start accelerating in the opposite direction. Okay. And also we came to know that it is 0 to 1 is the motoring mode, then if slip is between 1 to 2, it means it is in the braking zone. Okay. If at all a motor, if I say it is operating at a slip greater than 1, but less than 2, it must be in the braking zone. That is fine. Another interesting way of braking the electrical motor is called DC dynamic braking. DC dynamic braking. See, the ideas are very simple and interesting. Go through this idea, so that it will further enrich your knowledge of induction motors. This is done like this. See, suppose this is the stator of a induction motor. I will tell first verbally what is done, and this is suppose your induction motor rotor. I am sometimes drawing slip rings, sometimes cage. This is the rotor, this is the stator. Okay. Now, what you do, once again you have a switch okay, where you bring the machine terminals in the middle of that double throw switch. Okay. And here you connect your AC supply, AS, supply A, supply BS, supply CS, whatever it is. Okay, supply CS and supply BS you connect. So, it will be motoring mode. Switch is here, motoring. And on this side of the switch, what you do? You keep a DC source ready, DC supply, battery say DC supply. Okay. Therefore, when it is running as a motor, this is the situation is BSCS, and machine was suppose running at this speed NR as a motor, as a motor, it was running with a slip ns minus nr by ns, and there was a rotating field here, which was running with ns to f by p. Now, what I will be doing, first let us talk in language. What we will be doing, suppose this switch is brought it here, this side, and the third one nothing is connected. If AC supply, that is instead of AC supply, I now excite the stator, which was already running, the machine was running with speed nr with a slip this much. Now, suddenly what I will do, I will disconnect the AC supply from the stator winding and inject some DC current onto the stator. Therefore, suppose at t equal to 0, stator supply is changed to a DC supply. That is, this switch I will connect it this side. If you do like that, then what is the connection? This is the connection. There is plus minus DC, that is all. This side nothing is connected, suppose, and here is your rotor. Can rotor speed change instantaneously? No, it was still running with this speed at t equal to 0 plus. This is the situation. If you connect it like this, first of all, you see that DC current will flow. What kind of field the stator winding is going to produce? A stationary field, not moving field, is not. Suppose the number of turns of the stator windings are Na and some I DC is passed. Therefore, the MMF or field will be, suppose current enters through the start of this phase is N I DC, that divided by reluctance etcetera will give you H and hence B. So, N I DC, but for this fellow it will be like this, also same strength, but not away, because it is leaving the start of that phase. Therefore, resultant field will be like this, and this angle being 60 degree, the resultant field will be 2 N I DC into cos 30 degree, and that is equal to root 3 N I DC. So, the strength of the field will be fixed in space. This time this field will be created, but stationary in space, stationary. This stator field, what will be created, it will not be moving, it is not excited by AC current anymore. Therefore, its strength will remain phase. Okay, let it remain there, but here is a rotor which is already in running condition. Therefore, these conductors or wound rotor thing, whatever it is, there will be induced voltage in the conductors, and the rotor circuit is closed. Therefore, current will be flowing through the conductors, or the, if it is it will be easier to understood if suppose this is the rotor, either this or this is shorted. Therefore, there will be balanced 3-phase voltages, there will be balanced 3-phase current here, but it looks like it is acting as a generator, is not, because it was already running at that speed nr. you have a field here, there is induced voltage and there will be power dissipated as heat in the rotor circuit. That is what I am telling. If you want to, so the kinetic energy stored will be dissipated at a faster rate compared to the situation when you simply disconnect the stator from the supply. Disconnect the stator from the supply and quickly switch on to a DC supply, and then I am arguing okay, there is a field moving at a speed nr and there is a rotor which can be thought of as equivalent some star winding, we discussed cage rotor, whatever it is. There is balanced 3-phase current flowing and power is dissipated here. So, in which direction electromagnetic torque will be produced now? In case of generator mode, if it is moving it like this, the electromagnetic torque developed will be like that, is not? Therefore, electromagnetic torque developed by the machine will be trying to oppose the direction of rotation, and thereby its kinetic energy will be going on reducing. Of course, mind you, this speed nr with which we started at t equal to 0 plus is gradually decreasing, but at any instant of time the picture is this, okay, whatever is the nr that decides this one. Strength of the field, will it change? No, it is 2 n I d c by root 3 by 2. Therefore, I have now a situation like this. Now, to cast this problem in terms of induction motor theories what we have learned, I can see this as equivalent to, this situation can be analyzed as equivalent to this one. I will assume rotor stationary, and this field, this stationary field which was, this field created by this DC current is moving in the opposite direction with a speed nr. That is the situation. Let nr vary with time, but at any instant of time this is the situation. So, then I will argue that there is a rotating field whose speed is nr, not ns, and here is an induction motor. So, electromagnetic torque developed by this so called equivalent motor, electromagnetic torque must be this, and that is the braking torque it is creating. I can always think. See, these are the nice things, okay, that rotating field concept I can still apply. I will only argue that this field is moving in the opposite direction now. Earlier I assumed nr in this direction. So, that speed I give to the stator field and presume that rotor is stationary. So, it looks like for this induction motor I have to find out the starting torque or block rotor condition torque, is not. That is what, if I can find out, then I will be able to calculate the braking torque. Just to give you an idea what I am going to do in the next class, that first of all this stator field which is now stationary Fs, here also it is Fs, it is moving with a speed nr. Therefore, I can always attribute to this that okay, my balanced 3-phase winding is carrying a balanced 3-phase current of frequency P nr by 2. That is, now see, I am now switching over. Okay, I want to see that if you have drawn this, then I will argue okay, this 3-phase winding is connected to how this inner speed of a rotating field can be obtained by energizing the same stator winding with some AC source whose frequency is PNR by 2. That is this so called synchronous speed of this imagined motor situation now, with the hope that I will be able to calculate then the braking torque for this motor. So, this is the thing. But now what is NR? NR is, as a motor, NR is nothing but 1 minus S into NS, because when it was running motor at t equal to 0 plus I am considering. So, whatever I want to find out the braking torque right at t equal to 0 plus say, then this is the situation NR equal to 1 minus S. Then I will put it like this 1 minus S into NS, and then I will say this is nothing but 1 minus S P NS by 2 is when it was connected to frequency F stator AC supply, with that supply in terms of that. That is an induction motor which is now supplied with this frequency, and its rotor is stationary. I want to calculate what is the torque produced by it, and that will give me an estimate of braking torque. Therefore, I will invoke the equivalent circuit in the next class and how to calculate it. Easy, but the whole idea is why I am telling this way braking is also not done these days. DC supply, inject it, okay. But only good point about it is machine will eventually come to stop, no question of rotating in the backward direction. What will happen? When the speed will become 0, no induced voltage, no current in the rotor. Anyway, I will continue with this in the next class. Thank you.